This is going to be a review on chapter, or not on chapter 4, but this is the fourth review for stats, which is basically on probability. So we're going to go over the basics of probability, combinations, permutations, all that good stuff. So at its core, the probability is basically two things. Like probability can always be reduced down to one single item, which is this fraction, which is the number of things you want. Again, you have to ignore the bad handwriting here because I'm writing with my mouse. So the number of things you want over the number of total things. So again, think about rolling a die. If I want the probability of rolling a 6 on a die, well, there's one thing I want because there's 1 6 on a die, and there's 6 things that can happen, 1 through 6. So there's a 1 in 6 chance that I roll a 6. Now, that's pretty simple. The trick here is that sometimes getting these numbers can be quite big or quite difficult because of the way the situation is. However, you always have a guidepost in that. Remember, it probably cannot be less than 0 or more than 1. It always has to be between those two bounds. So let's look at sort of an easier case, which is when we have multiple events. So let's say I want the chance that if I flip a coin, roll a die, and draw a card, that I flip a heads, roll a 6, and draw the ace of spades. Well, the chance of getting a flipping a heads is 1/2, 1 head out of 2. The chance of rolling 6 on a fair die is 1 out of 6. And the chance of drawing the ace of spades is 1 out of 52, because there's one ace of spades out of 52 cards total. So it'd be 1/2 times 1/6 times 1 over 52. I would just multiply the different probabilities together. So if you want to figure out the likelihood of something of different events, you simply multiply them together. So 2 times 6 times 52 is 624. So 1 out of 624, which is a pretty low percentage, but still a percentage. Let me do a mic check here. Okay, it's going. So when you have multiple different independent events, all you simply do is you split it into as many categories as you can, find the probability of each different category, and then multiply them together. Now, this can also work for like the same event done multiple times. So what's the chance of rolling 4 times when rolling a fair 4-sided die? So if you have a 4-sided die that's fair, assuming that means we have 1, 2, 3, 4, and each one is equally likely to happen. So there's a 1 in 4 chance of me rolling a 4 on the first roll. There's a 1 in 4 chance of me rolling a 4 on the second roll. There's a 1 in 4 chance of me doing it on the third roll, and there's a 1 in 4 chance of me doing it on the fourth roll. So each roll is its own little event, and each roll has a 1 in 4 chance of rolling a 4. So it'd be 1 over 4 times 1 over 4 times 1 over 4, which if we do 4 times 4 times 4 times 4, or 4 to the fourth, or 16 squared, would give me 256. Right? So that would be the likelihood of rolling 4 times on a fair 4-sided die. So again, when you have multiple events, split them up into different categories, and then find the probability of each one, and then multiply, not add, but multiply those probabilities together. Now, if you're doing something without replacement, which is called a dependent event, then you still have to take them individually, but you might have to alter your fractions every now and then. So let's take this one here. So we have a bag that contains 3 red marbles, 5 golden marbles, and an eye. If 3 items are selected without replacement, which means when I take an item, I don't put it back for my next draw, what's the probability that we get a red, and then another red, and then an eye? Well, in total, we have how many marbles here? So there's 3 red, 5 gold, and 1 eye. So in total, it's 9 marbles. So my first draw, I want to pick a red marble. Well, there's 3 red marbles out of 9 total. So that'd be my first probability. My next probability, I want to draw another red marble. Well, if I'm doing it without replacement, that means I'm assuming this already happened, which means that I now only have 8 marbles left in the bag because I pulled out one of the red ones. And not only that, but I only have 2 red marbles two red marbles left because I pulled out a red one. So I already pulled out 1 red here. So I'm down a red marble and I'm down 1 total marble, so I have 2 out of 8. And then for my next fraction, well, if I want to pull an eye, there's only 7 things left in the bag, right? There's 9 things here. Then I pulled out a marble, now there's 8. Then I pulled out a marble, now there's 7. And only one of them is the eye that I want. So that would be my next item. So then it would be 3 times 2 times 1, which is 6. And then 8 times 7 times 9, which if I do quickly here on my hand calculator, 8 times 7 times 9, which would be, or 9 times 8 times 7, doesn't matter, would be 504. Which if you reduce it, that would be 3 over, let's see here, that would be 252. which I believe can also be reduced further to 1 out of 84. So this would be my final answer, 1 out of 84, or whatever decimal or percent that comes out to be. So when you have an event without replacement, which means that you have a dependent situation where past events affect the current events, that's when you take it as separate cases, but you include or you take into account the fact that each case might have been changed based on what happened before. So what if we have the probability that 3 gold marbles will be selected without replacement? Well, once again, I start with 9 marbles, of which 5 are gold, right? 5 gold marbles. Then I pick one. So now I have 8 marbles left, or 8 things left, because there's an I in there. And then now I only have 4 marbles that are golden. Then I pick that one. Well, now I only have I only have 7 things left, and now there's only 3 gold marbles left. So it'd be 3 out of 7. So it'd be 504 on bottom, and then let's see, 5 times 4 is 20, so it'd be 60 on top. So then you would reduce I'm not going to go bother reducing it because I know you guys can reduce fractions, but that would be your answer after it's been reduced, okay? So again, we take it as 3 separate cases, but each case is going to change the fraction of the following case. Now you can also do this with percentages as well. So we said that the shoe company here says that 4% of the shoes that it makes are defective. If we have 1,000 shoes and 3 are selected, what's the probability that all 3 are defective? So again, I have 3 cases here, right? First pick, second pick, third pick, and this is without replacement. Well, first off, what's 4% of 1,000? So if I have 1,000 and I times it by 0.04, that means that I have 1, 2, 3, so that'd be I have 40. So there's 40 defects. I forgot a C there, didn't I? I'll just leave it as 40. So there's 40 defective shoes out of 1,000 total. What's the probability that all 3 are defective? So what's the probability that my first one's defective? Well, 40 defective out of 1,000 total times, what's the next one that's defective? Well, in this case, I only have 39 defective shoes left. I only have 999 shoes in total. And then what's the probability that the next one's defective? Well, again, now I have only 38 shoes left, of which 998 are defective. Or sorry, 38 defective shoes out of 998 total shoes. I switched my wording there a little bit. So you multiply these together and you'd get your answer here. I'm not going to multiply these all together because I know you guys can do it. The n decimal, just in case you're wondering, so I'm not going to make it as a fraction because, like I said, I know you guys can multiply these numbers. Whoops, make sure I put a 0 in there. Times 999 times 998 would end up being 5.95, if I'm rounding, times 10 to the negative fifth. Now, in this case here, like I said, you'd first have to figure out how many defective shoes total you have. So you had to figure out what your defective ones were for first, and then you would plug it in there as fractions. So you didn't have the marbles given to you like in the first problem. Here you had to figure out how many marbles, or in this case shoes, that you need to have that are defective, and then you can use that as your situation. So again, each one is a case-by-case basis, but each case can affect the other. All right. So let's go ahead and this one here. So the FCP is a way of counting up how many different possible outcomes there are. Like here, we had 1,000 possible outcomes. We had 1,000 shoes to choose from. So we had 11. I keep saying 11. We have 1,000 possible shoes we can pick. Here we had 9 possible things in the bag that we could pick. Well, what if we have a situation where we have like a music contest that has 5 performances and we want to schedule them? So how many different ways can we schedule performances? Well, that's a little bit different than just counting up the number of outcomes because that's kind of hard to do. So the FCP says, once again, you split this into 5 cases. 1, 2, 3, 4, 5. How many performances can you put first? Well, any one of the 5 people can go first. So any one of those 5 people can be first. But whoever's first can't be second. So now once I pick the first person, there's only 4 people to pick from for the second spot. And then there's only 3 people left to pick from for the third spot. And only 2 people left for this one, and only 1 person that can be last. And then you multiply, not add, but you multiply all this good stuff together. So that'd be 20, 60, 120, so this would be 120. There's 120 different possible ways that performances could be scheduled in this situation. Now again, this is not asking for a probability. This is simply asking for the number of ways it can be scheduled. So it's not 120 out of anything. It's not 1 out of 120. It's just 120. That's it. Because it's just asking for how many different ways can you schedule them. But again, it's very similar to what we did. We split it into 5 cases and we figured out what happens for each individual case. Again, we're doing it as a case-by-case basis while realizing that, again, the previous cases might affect the following cases. Okay? So how many options can I put for each spot? What if a slot machine has 5 slots and each slot can display one of the 10 digits? So again, I have 5 slots. 1, 2, 3, 4, 5. And any of the 10 digits can be in these slots here. So how many different arrangements of numbers can occur? Well, you can have any of the 10 digits for the first one, and then any of the 10 digits for the next one, and then the next one, and then the next one, and the next one. So each one has 10 different numbers that can pop up, 0 through 9. And then I multiply all this stuff together, which in this case would be 1 with 5 zeros behind it. So 1, 2, 3, 4, 5. Yeah, so 100,000. And so, again, sometimes you have the same number multiple times. Other times you have different numbers for each case. It just depends on the situation you're given. This one here says, what if the slot machine has 10 different values for each slot? Like this is like, say, 0 through 9, and then the next one is 10 through 11, or 10 through 19, we'll say, and the next one is 20 through 29, and so on and so forth. So what if I have 10 different values for each slot of the slot machine? Well, actually, that wouldn't necessarily change anything, because how many numbers can go for the first spot? 10. How many for the next spot? Still 10. There's 10 different numbers, but there's still 10 numbers that can go for each spot. So 10 here, 10 here, 10 here. So I multiply these and I still get 100,000. So even doing this way, it's still the same case. Right? Because again, there's 10 values that can go in each spot. Now some of you might be saying, well, what's the difference between this one and this one in terms of permutations and combinations, which we'll get to in a second here. But in this case, I just said how many different arrangements, so I'm including the repeats. So again, I have 10 different values for each spot, so I can just do 10 times 10 times 10 times 10 times 10. But again, it doesn't matter if they're the same or they're different. All I'm looking for is the amount of stuff that can go in each spot. So here, there's 10 numbers that can go for the first, 10 for the second, 10 for the third, so on and so forth. And then here, once again, 10, 10, 10, 10. Here, it was 5 and then 4, 3, 2, 1. Because every time I pick a performance, they can't be in the next spot. So this was a dependent situation, whereas these were independent situations. Now, permutations and combinations are special types of arrangements. So they usually have formulas here called NPR and NCR, where N is the total number of things that you have. So that's the number of things you could pick from, and then R is the number of things that you pick. So you use these when you're not necessarily selecting every single item that you could. So, for instance, a committee has 31 people, but they're only going to pick 4 to be in the following positions. Right? So you have 4 different positions, assuming each person can be in each spot. So let's say that, any one of the 31 people can be a tank, any one of the 31 people can be an attacker, supporter, and healer. So anyone can fill any role. I have 31 people to pick from, but I'm only going to pick 4 of them. How many different arrangements can I make? Well, in this case, we're going to use an NPR because, not National Public Radio, but because the arrangement does matter. So let's say I have a person, we'll call her Farah. Okay? Okay? Farah, whatever you want to call her. Let's say that this person can fill any one of these roles. Well, if I pick her as a tank and then pick another person here, another person here, another person here, that's a different committee. That's a different setup. That's a different administration than if I put her here and then pick people over here. So this might be a really poor administration if she's a tank or something like that. Let's say that's one type of administration that you can have. Whereas here, if she's an attacker, that might be a better administration, or at least it's a different administration, right? So depending on where I put the P, I have a different end result. So if the order of the stuff matters, you use NPR. So in this case, I have 31 things I can pick from. I'm going to pick only 4 of them. So I'm going to be using NPR. So you go to your calculator. Once again, if you don't know how to do this, come on. You go to Math, PRB, NPR. Now, in this case, I have to put my number first. I have to put 31 first. And then Math, PRB, NPR. And then I pick 4. And that will give me 755160. So 755, comma 160. So again, all you have to do is just pick the right formula in your calculator and make sure that you have the NPR versus NCR business down, and you got it. What this really does, by the way, is it does what we did in the before, right? It splits into 4 cases. 1, 2, 3, 4. Well, of the 31 people, how many can be the first person, can be the tank? Well, any one of the 31 people can be a tank. Well, if this person's a tank, they can't be an attacker. So now I only have 30 people to be an attacker. Well, if this person's an attacker, and I already have another person for a tank, that means I only have 29 people that can be support. And then after that, I only have 28 people that can be a healer. And if I multiply these together, I get back to this number. So all NPR does is it does the situation. It splits it into 4 cases, and it does 31 times 30 times 29 times 28, or whatever number you have. It does the same pattern. So you can do it without the formula as well. It's a pretty simple one to do by hand, but just so you know what's going on behind the scenes there. But again, the key here is that if I put somebody in a different spot, it's an entirely new different outcome. Whereas NCR is used when you don't have a different outcome. So for example, if you're picking cars to display, so you have 20 cars to pick from, you want to pick 4 to display in the store. Well, that means that if I pick, say, or sorry, in this case the order doesn't matter. So if I pick, say, I have 4 spots, right? If I pick, say, a Subaru, so let's say a Subaru, I want to be the first car I display. And then I pick, a Toyota Camry, we'll pick a Jeep here, and then we'll pick, I don't know, a Corvette here. I'm just picking cars that I know, which I don't know a lot of cars because I'm not a car guy, but I'm doing my best here. So that's one display you can do. Well, if I picked the Toyota first, and then I picked the Jeep second, and then I picked the Subaru next, and then I picked the Corvette last, this is still the same display, right? I still have the same 4 cars on display. It doesn't make a difference. So if the order doesn't make a difference, if there's no special rule for each position, then you use an NCR. So I have 20 items to pick from. I'm going to choose 4 of them. But again, I'm choosing, which means that I'm not counting these as 2 different outcomes. This outcome here is the same outcome as this. So I want to divide out the repeats. And that's what NCR does, is it divides out the repeat for you. So you have 20, math, PRB, NCR, and you're going to choose 4 of them. So you have 48, 45. So 48, 45, right? So again, you use this when the order of your stuff doesn't matter. It doesn't matter if I pick the Subaru first or third, it's still going to be on display anyway. Okay? So pick for P if the position matters. So pick means position matters. P means position matters. Whereas C means that it doesn't matter. So C means you can choose any spot you want for it. It's going to be the same outcome no matter where it's at, right? All right, so then other times you might have a table of stuff you need to work through. So this is more earlier stuff. So we have 3 creatures here, and they're gauged on how likely they are to attack humans. So we have 16 werewolves. 4 have a low chance of attacking humans, 10 have a medium chance, and 2 have a high chance. And then same thing for chupacabras and sasquatches. So if we pick one of these people at random, or one of these beasts at random, what's the probability that we pick a werewolf that has a high likelihood to attack humans? Well, let's first look at the total number here. So let's add all this stuff together. So 4 plus 10 plus 2 plus 12 plus 4 plus 1 plus 3 plus 5 plus 16. I'm going to add all that stuff together and get 57. So there's 57 total things I can pick, 57 total beasts I can pick from. If I pick one at random, what's the probability that they are a werewolf that has a high likelihood to attack humans? So we're going to say this as that has, we're going to say this, we're going to assume that this means and, right? So a werewolf and high likelihood. Werewolf and high likelihood. So that means that I want exactly these 2 things. I want a werewolf and a high likelihood. So there's 2 werewolves that have a high likelihood out of 57 beasts total. So 2 out of 57 would be my answer there, or whatever decimal percent that comes out to be. Because again, and means I want the single value that satisfies both conditions, werewolf and high likelihood. Whereas if I say or here, so a Sasquatch or having a low likelihood of attacking humans, well, that means that I could be either a Sasquatch, which are all these values here, so 3, 5, and 16, or I can pick at least something that has a low chance of attacking humans, which is these up here. So I'm going to add up 4 plus 12 plus 3 plus 5 plus 16 out of 57. And then if I add all those up here, let's see, 4 plus 12 plus 3 plus 5 plus 16. I get 40. So it would be 40. Make sure I did that right there. Yeah. So it'd be 40 out of 57. Because again, or means I can be any of the first category or any of the second category. It's not a restriction, right? Or gives me options. If I hear the word and or something that implies and, that means I'm restricted. I only want to pick the single value that satisfies the conditions I'm looking for. Now, the last one here is more of a given situation. So what's the probability that they have a high likelihood of attacking humans given they're a chupacabra? So given means I'm limiting my total number here. So given means that the bottom number here is going to change. So given they are a chupacabra, which means that I don't care about these, I don't care about these. All I'm looking for are the chupacabras. So in this case, I have 12 plus 4 plus 1, which would be, let's see, 12 plus 4 is 16, plus 1 is 17. So I have 17 chupacabras, right? That is the number of chups, C-H-U-P-S, number of chupacabras. I want to pick, of these 17, I want to pick the one that's a high likelihood. So that's only one of them. So there's only one chupacabra that's a high likelihood of attacking human. They go for goats more usually. So this would be a 1 out of 17 chance. This would be my answer, right? So when I hear the word given, that means I want to limit my scope. I'm no longer going to be out of 57. I'm going to be limited out of 17 here because I'm focusing just on that one category. Right? So that's the and, or, in given situation. And means you want to pick one number from the entire table, or means you're picking multiple numbers from the entire table, and then given means you're narrowing your scope into just one row or one column of the table. And then sometimes if you want to go backwards, like doing at least probabilities, getting the direct answer is a little bit difficult when you're doing at least. So instead we, again, work backwards. So we're going to do something called finding the complement. So complement. And what that means is that we're going to find the probability that something does not happen. That's what the complement means, do, something that does not happen. And if I figure out the chance that something does not happen and I subtract that from 1, then I have the chance that it happens at least once. So for instance, what's the probability of rolling 4 on a fair 6-sided die? What's a 1 out of 6 chance? What's the complement? Well, that'd be 1 minus 1 out of 6, or 5 out of 6. There's 5 chances of not rolling a 4 out of 6 chances total, or 6 numbers total. So if I want the at most or at least problems, I can use this fact here to solve for them. So let me give you an example here. Let me put some numbers to this. So there's 1,000 presents under the tree. 800 presents contain a moon rock. The rest contain a rabbit foot. If 3 are opened at random, what's the chance that at least 1 contains a rabbit foot? Well, that's a problem because at least 1 means if I have 3 spots, I can have the rabbit foot here and then missing both of these. Or I can have the rabbit foot second, or I can have the rabbit foot last, or I can have the rabbit foot first and second, and then miss the third, because at least means I can have 1 or more. So I can have it like that. Or I can make it have R, X, and then R here. So there's a few different ways this can happen. There's so many different ways that this could happen that trying to figure out directly is difficult. However, there's only one way it cannot happen, right? If I want at least 1, that means the only way that does not happen is if I have 0. Because 0 is the only case where I don't have at least 1. So I'm going to figure out, okay, what's the chance of me having no rabbit feet picked? Well, if there's 1,000 presents and 800 of them contain a moon rock, that means there's an 800 in 1,000 chance for my first one. And then there's a 799 out of a 99 chance for the second one. Because, again, if I open a present, I can't open the same one twice, right? So this is without replacement. And then I have a 798 over a 998. So I'm going to multiply this out here and get a decimal answer. So 800 times 799 times 798 divided by 1,000 times 999 times 998. And I get 0.512. 0.512. So there's about a 51% chance that none of them contain a rabbit foot. Which means if I want at least 1 rabbit foot, I would do 1 minus 0.512. And I would get 0.488 if I did my mental math correctly, which I believe I did. Let me just check here. 1 minus the answer. Yes. So about a 49% chance that at least 1 contains a rabbit foot. Because what I did here is I took 100%, which is the chance that something happens. and I subtracted off the chance of what I don't want happening. So this is the chance of something I don't want. So if I have everything, and I subtract the one thing I don't want, I'm going to be left with the one thing I do want, which is at least one rabbit foot. So again, getting the probability directly here is troublesome because there's so many different ways it can happen. But getting the one chance it can't happen, and then simply taking that away, is a lot quicker and easier to do than trying to do it the other way, than trying to go directly. All right, and so lastly, we have odds here. So odds are different than probability in that they do not use the total amount. So there's two ways to think about odds. Okay? So the odds against something happening. So the odds of against A happening is the probability that A does not happen compared to the probability that A does happen. Now, what this essentially boils down to is the number of ways. So number of ways for not A compared to, usually not written as a fraction, usually with a colon, compared to number of ways for A. So for example, rolling a die. What's the odds against odds against picking A or rolling a 6? Well, how many different ways can rolling a 6 happen? Well, there's one way to roll a 6. So there's one way to roll a 6. And there's 5 ways to roll a not 6. So the odds against 6 happening is 5 to 1. That should be a colon there. There's 5 not 6s to 1 6. So you could do this probability as well. You could say that there's a 5 in 6 chance that it does not happen, and a 1 in 6 chance that it does happen. But what happens here is that the colon kind of acts as a fraction, and the denominators cancel. So this 6 cancels with that 6, and we're left with a 5 to 1 anyway. So I just usually write it as 5 to 1 without writing the fractions involved. And the odds in favor is just flipped. So the odds in favor are the way that A does happen versus the way that A's do not happen. Right? And again, you can use the ways rather than the number of probabilities here. So let's do an example here. So we have a true-false question that has 5 questions, and a student must get all 5 correct to pass. So what are the odds in favor of passing? What's the odds against passing? Well, let's figure out the probability way first, and I'll show you. So the probability of passing. Well, if he needs to get all 5 correct, and they're true or false, it means he has a half a chance of getting each one correct. That's going to be 1/2 times 1/2 times 1/2 times 1/2 times 1/2, right? That's the chance of getting all 5 correct, right? Because you have a half a chance for each problem. So it'll be 2 times 2 times 2 times 2 times 2. So 2 times 2 times 2 times 2 times 2. 1, 2, 3. That'd be 32. So there's a 1 in 32 chance of him passing. Well, what's the chance that he does not pass? So not pass. Well, again, using complements here, if there's a 1 in 32 chance of passing, because he needs to get them all correct, that means that there's a 31 in 32 chance of him not passing, right? Because, again, they have to add up to 1. So there's a 1 in 32 chance of passing, 31 in 32 chance of not passing. So the odds in favor are 1 to 32 to 31 to 32. But as I said, what happens here is that the denominators cancel, and so you end up with 1 to 31. There's one way to pass, and there's 31 ways to fail. Because again, if you get one of them wrong, you fail the entire thing. So if you get 1 wrong, if you get 2 wrong, if you get 3 wrong, if you get 4 wrong, if you get 5 wrong, you fail anyway, and you can get any one of them wrong. So maybe you get, the first one correct, but then the other one's wrong. Or maybe you get the first one wrong, the next one wrong, and then correct, and that'd still be a failure there. So there's only one way to get them all right, and there's 31 ways to not do that. And the odds against would just be the reverse. The odds against would be 31 to 1. Because there's 31 ways to fail, there's 1 way to succeed. Right? All right, so that's the end of this one here. Again, there's a lot more calculation information in this one than the other ones last week. So like I said, if you need help or something, let me know, and I can expand on these further. Otherwise, hopefully this helped you out. Look forward to seeing you next time, or hearing you next, or you hearing me next time, whatever you say there. Anyway, just have a good day.